A wonderful good Saturday morning. Let's be lazy and see what we can get for free. There are a few things we do get for free. Software gets faster without touching it, simply by hardware getting faster. Software doesn't do anything, it's obviously hardware doing anything, so if the hardware gets faster. Software tends to get faster as well. Core counts go up, clocks go up, IPC goes up, and it all multiplies. It doesn't stack, it multiplies, so that's great. However, there is kind of a blind spot, a hidden dimension in that equation. For about the last 30 years, vectorization has become a thing. So the CPUs don't just operate on scalars anymore. They can do a number of values at the same time in a single instruction. So today up to 16 typically. Right. That's all good and well. However, it's not covered by the C++ type system natively as such. That still is in the 70s and tries to operate on a PDB 11, I think. Which means that up to 90% of the performance might be left on the table if no magic happens between the code and the machine somehow. Right. So we are missing that last factor here, and that is quite significant, as that maybe an order of magnitude that could be untapped. Right. So why do I care? Well, I care deeply about performance. I hate it to wait for the computer if I know it could be instantly answering my commands. And it's also my job, so I'm a bit biased maybe. But I need to concede that vectorizing things by hand can be very tedious and overall too expensive, given the somewhat mediocre gains if you have many hotspots and you would have to go through all of them until you get a decent improvement. So automation would be great. And the good news here is that with the latest vector instruction sets on Intel and same on ARM, we get an interface that's much easier to code towards from the compiler's perspective. It doesn't have to do all padding to 16 elements at a time. It can basically instruct it to be quite like scalar, just have odd numbers of elements and all that. That's now enabled, so it should be easier for compilers to vectorize. And this year, GCC and Clang enabled auto-vectorization already at standard optimization levels. So O2, what basically everybody uses, they get that, and it's how I actually got triggered to maybe give a talk on that. And what I try to answer today is, will the compiler do all the work for me? Will it fail sometimes? When will it fail? And we will focus on simple code where there's good chances. So, STL algorithm like loops. Go over an array, do stuff. And I will also look at how much vectorization could give me if I had a perfect compiler or a perfect implementation, just to see how much is still left on the table after the compiler did its magic. Oh yeah, and none of that is a critique against GCC or Clang. They're all great, so just looking at what they're doing at the moment. For the one guy in the room who doesn't know what vectorization is, it is basically like loop unrolling. You have a loop body like on the left, two arrays as an input and an array as an output. You take one element at a time, write the result, go to the next one, and loop and loop and loop. And if you tell it to be faster, it's often with unroll, so it gets a bunch of things, then does the operation, writes a bunch of things. That is more code, right? It's bigger, it has to write the body 4 times, but we're saving on am I there yet operation. So the actual looping part is less, so that tends to be a bit faster. And vectorization almost does the same thing. It just operates on that as if it was a single value. So it has these lanes and then does the addition on every lane in this case. So every instruction does more. It's not a clever trick. It's about as many instructions at the beginning, just I get more output from each. And that also means the code size can be similar to the original one. Not quite, but closer to that. If anybody cares, all the examples, slides, and everything are in this repository. Right, let's start simple. So we'll all follow the same pattern here. The OG example for vectorization is high-performance computing. So the structures behind it are very well known and also quite regular. A vector is really very, very simple in the math, and matrix the same. And it's not relevant for your credits, but for your benchmarks. So everybody tries to be very good at that. So we would expect, if you have linear algebra in your code somewhere, maybe you need to transform graphical data from one space to another or something. You can expect that to be quite fast. And that's our test code, really simple matrix multiplication, nothing fancy about that, or scalar. If you have anything bigger than that, please use an optimized library for it. But if you have kind of a casual code that needs a 4x4 matrix times vector, that is something that you may have in your legacy code base, and it would be good to know how much you gain from that. And my expectation would be, actually, we get to the hardware limit. In my case, it would be 32 floating point operations every cycle. Okay. Right. Compiler Explorer, and if everything works well, then we see. Yep, that's it. So that is what it should look like here at the bottom. It basically loads the whole matrix, and then just has a single loop doing back-to-back operations. Every operation is 16 multiplies and adds it rolled into one and all the magic. So that will execute very quickly. It's zero overhead, kind of, sort of, a bit of counting here at the end. But it only works in GCC if it can resolve the original address somehow. I know that it stumbles. If I have a normal, if I have the actual original code that takes 2 parameters, yeah, it doesn't get that one side is constant. It loads it over and over again. For no obvious reason, it just does that. It would be the exact same code if it could see through that. It just doesn't. So GCC has a bit of an issue here. Clang seems to always get it right. All right. So linear algebra is good. And for all the examples, we will have a result slide like that. That overview, there's always a 1-0, that's a baseline, usually GCC 03 until mentioned otherwise. And the bottom line is what I guess would be the hardware limit, and then see where I can go. I always write a manual code, manual example, that gets more or less close to the hardware, not always. And then you can see, even at 02, Clang already gets to the limit. GCC sometimes fumbles a bit, but if you can see through things a bit better, then it also gets to the limit. And scalar, there, yes, you see there's a difference between 02 or 03. Okay, good. For completeness, the flags always the same. So what did we learn? Well, expectations have been met. It's all good. And we see that Clang is at 02 more aggressive in optimization in general. That's what I've seen in many of my examples. So that's what we have. And there will be another thing that's important to explain. How do we rate the speed up? Yes, we could do percentages or something that's a bit meh. I go for log scale. If you have a potential of 16x and you get to 4x, that's halfway because there's 4x on the table. So that's the log scale. If you get to 8x, that's 75%, because then there's only 2x left. That seems to be the most fair rating. So here we are at 75% at least. Under good conditions, depending on circumstances, you even get optimal results. Great. That worked. Let's be a bit more complicated. Structures that are still kind of regular, but have an odd size, for instance. Where you have a structure like here, red, green, and blue, 3 channels, and you need to extract them. Basically, you're having one struct. Yes, you have many of those structs, but from every one, you only need one element. So you need to pick things and put them back into vectors to actually do vectorized things with that. That's a bit fumbly, right? And of course, the size of the vector may not align with what's internally happening, or the size of the inputs and outputs. So there may be also a tail. So do leftover odd bits in a separate loop. All right. Go away with the, yep, that's good. Yeah, so you could also write the same thing as a transform, to transform something, except that Clang has a bit of issues then. Right. The weird thing is, yes, here the inputs is 8 bits, elements, but that operation is also wider, it's 32 bits, it's a float times, that needs to become a float. So it needs to be able to just not take a bunch, but also change the size of it, split it up into 4 bunches. For instance, I have an illustration done for that, what needs to happen. In optimal implementation, I had to look it up how to actually potentially do that. It would be something like 6 cycles per number of pixel. What the compiler will do, it will have to shuffle data around, it needs to extract the specific planes from the input, so all the greens, all the reds, all the blues, then also make them 32 bits and so on. So it needs to shuffle things around. And there is a magic instruction that can do a lot of that, and it's called permute, that allows you to put any byte anywhere and at any amount of times. So this is the perfect mapping operation, and the compiler knows about that, as we will shortly see. So short illustration, what would be an optimal implementation? I get my input, the red, green, blue thingies, and I extract the lanes and also widen them up. In AVX 512, I get 512 bits, as the name suggests, and that means I can have 16 elements in each vector, which also means combined only 48 bytes of input that I can actually reasonably process. So I would be optimal to just read 48 bytes, then do the vector magic, and then go to the next 48 bytes. However, that requires us to mask the read. The read has only read a bunch, and that's 64 bytes. I can now, in AVX 512, specify only actually read the first 48 bytes of that, and don't touch the rest, which is very important at the end of the buffer, for instance. Right? You don't want to grab data behind what's actually there. Yeah. All right. So we need to do this shuffle, and my personal expectation would be it kind of does it 2 steps. At first, gets all the bytes out, so makes red, green, blue, and then widens it as we did in the code instead of folding that into a single instruction. All right. So compile explorer time. Second page. Great. What we can see here, the implementation is not non-trivial, right? It goes on. It's like 3 kilobytes or something. Let's go to the first interesting bits. That's this one here. That is kind of the main loop. It goes on for a bit, so kind of one block, that's one main loop. It reads 3 times 64 bytes. Basically, instead of 48, it does 4 times as much, and then it aligns again with full vector chunks. That's why it does that. But it means also that it needs to process 4 times as much data, which means it needs a lot of operations. And here are the permutation instructions. It basically shuffles data around and permutes. And much further down, it will probably do some operation eventually. Yeah, here. That's the actual calculation. Everything else is shuffling data around. And the odd thing is that's still faster than doing scalarly. Right. And the reason why we have so many blocks is that the other blocks are for 32-byte and 16-byte at a time, kind of all the special cases that you can think of. It would be better if it would just say, read as many bytes as are there yet, or still there. You can do that with mask loading. And then we could completely eliminate all the other special cases. We'd just go for the first case and say, do I have more than 48 bytes available? Good, I'm loading 48. Otherwise, I'm loading as many as are still left. And then everything else just zeros that I put through the machine, but it doesn't bother the I/O. Okay. Goody. So what does it give us? So we could have a significant speed up. That's great. If I hand code it, I get close to that. And the vectorization is pretty good, about halfway. We've seen that there is all these peeling codes without clever masking, and we don't do a single element load. We load 3 chunks at once and then shuffle things around. So it always tries to find a common multiplier, I think. Yeah. Interestingly, Clang uses a different vectorization strategy, but that's just details. So we're still getting good speed up for that. So it's a non-trivial operation on a simple inner loop. So that vectorized quite well. Now let's go 2D. I have a blog post on that on LinkedIn if you're interested, go more into details. That's the implementation of std find first, verbatim, minus I shortened the identifiers a bit to fit on the page. So very boring. I have a source string, and then I want to find the first position that has any of the to find elements in it. For instance, if I have a string, I want to see, do I need to escape it? Where do I need to escape it? I look for the characters that need escapement, and then run the operation. It will tell me none or here. So it's a nested loop. And nested loops are problematic in 2 ways. First, yes, you want to vectorize the inner loop typically because that's the one that gets most executed, obviously. However, if you nest deeply, then the inner loop cannot execute that often, otherwise you would never terminate it because it's just too much work to do overall. So nested loop, the inner loops tend to be short. That's bad for vectorization. If in this case, for individual characters, you want to read 64 bytes at once, that's a lot of iterations already that you try to capture in a single vector instruction, and you may just run out of things to do. So yeah, that's a problem. Also, strings are special in many ways, but in that case, many string operations have clever ways to implement them that don't look like that. Look at tables, because the set of characters that we have is small, like 256, and the strings tend to be tens, hundreds of thousands of bytes. It makes sense to create lookup tables on the way, and then try to leverage that somehow. So that's the case here as well. I will not go into that. Whenever you do go for string operations, get some library that does it for you. It would be nice if libc had that specific one. It doesn't, apparently. But what you could do, you could provide a an overload in your system for this specific operation for strings, and also be much faster than whatever the compiler can do here. I would assume that if you're doing very well and the to-find gets very long, you might get close to the hardware limits. And the hardware that I run on, AMD Zen 4, you can do 64 comparison every single cycle. So you can run maybe 100 times faster than a normal scalar implementation. And the clever implementation can be several thousand times faster. So let's see what the compiler does. Stuff, right? So yes, it does vectorization. Yeah, here it's already marked. That thing L7, that is the inner loop, and it does vectorize compare large register against something in memory, and then checks, is the result 0, yes, no, and so on. So it tries to do the generic thing of vectorizing the inner loop. It's just that we know for reasonable use cases, the string p will just not be long enough to make that viable. So it will actually mostly execute the things at the beginning which say, figure out what to even do. That is one issue with vectorized code. It first needs to figure out, is the problem big enough to even call the vectorized code, and then it does the vectorization, or it will do something scalar again. So you always pay this overhead, which means vectorization can make your code slower, potentially. Okay, so yeah, that's code. So it does vectorize, so let's see what the result is. And I picked 2 cases, both very long source strings. One only has 5 characters to look for. That's the escapement use case, and that's been the only other use case I could think of that would be long. That would be everything that's non-control ASCII 7. So and then everything else should be figured out. Here we can see, yeah, the speed up that the hardware could give us is 60-ish. Okay, that's what you can see. If we vectorize the inner loop, we still only get like 20 times as fast, because that number is still not much bigger than the vector size itself. So there's lots of RB there yet already. So it only gets the loop twice, and then needs to handle the tail, and that every single time for every character. Lots of overhead, so we don't get very much. It's much faster if we would actually vectorize the outer loop instead of the inner loop, because the string is much longer. So I can always take big chunks of that and then do the inner loop normally. Right. What we've seen in code here, even in this good case, get a 4x speed up. That's not nothing, but compared to the potential, it's a bit meh. It gets much worse if we have shorter strings to look for. There again, the speed up is much more extreme. And we can see that Clang actually produces better scalar code than GCC. And auto-vectorization, because of all the checking overhead, is counterproductive. We actually get negative gains. Yeah, Clang in that case also decided to not vectorize. I don't know why specifically. So what metric would have been going into that, but it did not vectorize. Yeah, and again, to make that efficient, you would need masking. Right? You need to say, I don't care if you're looking only for 5. Give me those 5 bytes. I do this at once, and I don't require 64 every time. Give me what you have, but that requires masking, right? And also, what would be an interesting thing, something the compiler could do, it could actually check whether the inner loop or the outer loop is the bigger one, and then pick the bigger one to vectorize for. You can see it's actually, yeah, we get a bit of vectorization. If we compare to an optimized implementation, which is also in the repository, then we are way off. Good. Now, the last example. As you can see, the scheme is going downhill, right? Here I'm trying to give it as much leverage to optimize. I'm telling it those are really non-overlapping buffers. Try to do your magic. Code like that is surprisingly frequent in vectorized code. So what you're doing is you do your thing, you have your large input vectors, you're operating them, and then you need to make a decision. You filter things out, or you split them into two sets, left, right, and the condition is something that's not predictable at compile time, is something that you figure out as the data comes in. So what you want to do, you want to basically take a vector, remove a few elements, compact it, store it, and then continue with a compact set of data for the next step. So you don't have these gaps in your data where you have a mask that says, okay, only every third element, and then later even fewer and fewer and fewer, and become less and less effective. You want to be always operating on data that you actually need, so you need to compact that. And that's what you try to do here. In this case, I try to remove everything that's not a positive float. All right. Quite clean. What makes it hard for a compiler is it's not just masking. I think that would the comparison it can get. But after compacting, it forgets, or it doesn't track anymore the mapping between what's in the vectors and what's in the scalar code that you wrote. So the mapping, what you actually want from your code and what the compiler is producing, that gets lost. Because now your data is somewhere, but it no longer directly obviously maps to its inputs. So that seems to be hard. Although it's exactly what I want. I want the outputs to be the different ordering, but here it's intuitively clear that it's not an easy task for a compiler to say, yep, sure, I can just compact that and it will be the right thing. Yeah, so I expect it to fail. If you do vectorize it, you can actually be quite fast. You can do in a single core like 100 gigabytes per second in that code. It's mostly limited by how fast can I store unaligned data. And that's what we actually want to do as an illustration. Short vector, we just pick some element of them and then have them in one go. And we would have more vectors and would just put them here, append that here, and then continue with the data that we want and ignore all the rest. It's gone. It doesn't cost us any compute anymore. And there is a single instruction that does that. These are the intrinsics that you can use for vectorization. They all have these very obvious names. But it's a single instruction that does all the magic in one go. Just the compiler can't or doesn't use it. All right. Okay. Up, not there, here. Yeah. The first code that fits onto a slide, great. Yes, it's still using technically vector registers, but it's only because the floating point unit is part of the vector unit. Here it's doing single floats, SS. So this is really just a scalar loop. Yes, it's tight and quick for what it is, but it doesn't vectorize. Good. Yeah, so the results are not particularly surprising, except Clang is doing a better job. For whatever reason, the Clang code is running faster, even in O2. So there's not a big difference between O2 and O3 for both compilers, just Clang produces faster code. So something, yeah, unrolling, there it is. It unrolls the code a bit. So that's the OG trick that I showed at the beginning. And that seems to pay off in this case, so great. And yeah, we don't get anywhere specifically. Good. Those are the examples. For completeness. So one use case, why am I looking at that? You may have a legacy or just existing big code base. You don't want to rewrite it, or can't even. And does it make sense to recompile? Now that we've seen vectorization, at least in some cases, kicks in, yes, you can do that. But since you recompile, does it make sense to change your settings as well, maybe? Go from Clang to GCC or back, or go from O2 to O3. Does it make any difference based on what I measured in my setup? And I picked as baseline GCC O2 because that's probably the standard settings for many projects out there. And we can see at O2, going to Clang quite often has a significant speed up, except for these yellow ones. That's where I hand vectorized code. And there's so interspersed vector operations, and it sometimes doesn't seem to like that. It interferes with what it thinks about particular masking. So GCC doesn't have that problem so much. There's no big difference in Clang between O2 and O3. However, GCC has a speed up. It often catches up to Clang, and sometimes it's better, this specific one, but that's the only case where it's significantly outperforming Clang. So yeah, just for completeness, because I have the benchmarking data anyways. So I found it surprising that Clang is actually better. And well, the fair statement would be probably they moved more optimization steps to O2. Good. So what did we find? Yeah, as I said, Clang seems to be, at least for my examples, a bit more performant than GCC. Stumbles less. And in general, if your code happens to have lots of boring loops, then vectorization probably works quite well as of today. If it's more complicated, deeper, then maybe not. But yes, there is something to be gained at the moment. And if you're doing linear algebra on small problem sizes, then you can expect even perfect vectorization. So if you need Kalman filters, whatever you may have. In GCC, as we've also seen, you often may need O3 to get full vectorization. It does vectorization at O2, but way more conservatively. My interpretation is it tries to keep the code size at a reasonable, while GCC has no problem going all in. And if you go for O3, then GCC, as we've seen, is happy to generate kilobytes of code for a single function. And if you do it all over the place, it will get you the important ones, but also a lot of the unimportant ones, and that may actually drag down your performance overall. So that's a bit of a trade-off. My impression is also from other projects that GCC is slightly better at dealing with AVX512 code, particularly with masking. The masking bit, Clang will often replace even the intrinsics with non-masking operations and then add logical operations to the whole vectors, XOR and whatnot, instead of operating on the masks. That's a bit weird sometimes. So if I were to develop GCC and or Clang, for me, the next meaningful step would be implementing mask loads and stores, so that you don't need peeling loop, so the odd one at the end for all the scalar bits that you could fit into whole vectors. If you could just say, whatever the number of elements is, load them, and the rest is zero. I go through the machine and then store only the results that are relevant. If I can do that, I'm much faster than I'm right now, because I can vectorize almost everything without creating much of code overhead. Mask operation in general, it can do a bit of that. What it often will not do is actually Boolean operations. So you do comparison, it has to do a mask because that's what the instruction says. So you compare two vectors, you get a mask. But if you then combine that result with something else, that doesn't happen. It doesn't use the masking operations for that. And then we had this example of which loop is the right one to vectorize. I guess there's also a few very specific cases, but they're still frequent enough to justify a special treatment in the compiler where we look for which level is the exact level, the correct level to vectorize and go for that one. Right. So yeah, overall we get quite a bit for free. And there's still stuff to do for the compiler writers, which is good for their job security, I guess. So, and that would be the end of my talk. Questions, please. Yeah. There's one in the back. Sorry.
I saw that C++26 is supposed to have like these new SIMD extensions. Have you any experience with the hand vectorization using those?
I don't have that, no. Yeah. I haven't even looked into that specifically, how much is provided by the libraries already. Yeah.
Yeah, thank you for the talk. So, given the state of masked handling of the tail of iteration loop, could you still recommend to do some additional stuff on the client side, just to handle the loop, giving the SIMD lane size? So, for example, we just check if it fits to SIMD lane in our integer, and then we do the rest in another loop. So, does it matter nowadays?
It does, particularly for vectorized code. I have all the examples here.
The 13th slide.
Yeah, which one is it? It would be, the RGB one, for instance. Oh, yeah. Well, that's one way of doing it. Basically, you only have a single loop, and then decide whether you do a. You always do a mask load, but in the last iteration, you would pick the shorter one. That's often good enough because you have enough latency in the system to not make that bit count. In other cases, actually better to have the main loop doing non-masked aligned loads, and then only a peeling loop that's basically just one loop body doing the masking. Personally, I would say that is a better solution, even if it costs you some performance in some cases. It's like the difference between a 12x and 16x speedup versus not having a speedup at all, maybe. So that's probably the more. I'm happy with the more generic, slightly worse implementation. So, okay.
Thank you.
Do you encounter some possibility to improve the code itself? So yesterday I heard the talk from Jonathan Müller regarding cache-friendly C++. Does some of the suggested changes impact the ability to vectorize?
Yes. The cleaner your data structure becomes, so that if it's containing exactly the data that you process, then you're back to basically linear algebra, where you have a plain old vector. All the things in there are exactly your numbers that you need. Yes, I would expect that to be much faster. It is very hard to pull off, in a sense that going from array of struct to struct of array is a significant rewrite of your code base. So it's not for free. Yeah. More question?
Thank you for great talk. There was already a question here about the standard library implementation of some vectorized framework. Do you have some thoughts maybe on Google Highway or other frameworks? Because whatever you do in here is compiler/processor specific, depending on how you do it. I think this would be a good thing to abstract out, to have broader support, maybe different architecture like ARM.
None of what I did here is, the measurements happened on a specific machine, right? That's architecture specific. But the original code is standard plain scalar C++. So I would expect it to produce the same compilers to produce similar code for SVE2, so the modern ARM platforms. I haven't checked it, so that should work. And beyond that, yeah, I don't know what other compilers will do. I haven't checked that. I've been working with embedded compilers quite a lot, and they tend to vectorize much better if that's what the target needs. But yeah, I didn't look into the Google frameworks here.
Thank you.
Okay.